here right now, which is to talk about our first invited speaker, which is Yasunobu Nakamura from Tokyo in Japan. Yasunobu Nakamura is director of RIKEN Center for Quantum Computing, and he's really an expert in a wide range of quantum physics using superconducting circuits, which he will talk about today. So please, everybody, please give it up for Yasunobu.
Okay, good morning. Goedemorgen. So thank you, Christian, for the kind introduction. And also, I'd like to thank the organizers for giving me this opportunity. This is my first time in Veldhoven, even though I've been in Holland many times. So let me start. So actually, I spent a year in Delft a long time ago, 20 years ago, in Hans Mue's team, working together with Kees Hermans and Caspar and other guys on superconducting qubits. So yeah, that was a splendid year for me, and we really enjoyed the stay. And so, yeah, and okay. So, yeah, at that time we worked on this flux qubit device, and I found that this is really 20 years anniversary of this flux qubit experiment paper. So maybe that's why I was invited here. Okay, so today I'd like to talk about superconducting circuits for quantum technologies, mainly using superconducting qubit, resonators, waveguide, and so on, for different purposes. And so let me begin with say history of quantum mechanics. So as you know, quantum mechanics was born at the beginning of 20th century, and then formulated by 1920s by Heisenberg, Schrödinger, and other guys. And then immediately after that, people started to apply quantum mechanics in every direction of physics. So for example, in condensed matter, band theory was established already in 20s, surprisingly. And then later in other fields like quantum electrodynamics and particle physics and so on. And by now, quantum mechanics has been applied to many different fields, from particle physics to atomic physics, condensed matter physics, transistors, lasers, and even the whole universe is considered as a, behaving as a quantum mechanics influenced by the quantum fluctuations. And so, yeah, so our daily life, our information technologies fully rely on quantum mechanics. But, yeah, and for example, this is the famous Moore's law. Maybe you have heard that recently Gordon Moore passed away, but he must have been very happy to see his famous law has continued for more than 50 years, from 1965 to now. And now we have more than a few hundred billions of transistors in one chip of silicon. And thanks to that, and actually this is, I believe that this would not have happened without quantum mechanics. And thanks to this progress in the semiconductor technology, and also the technology for integration and architecture, now we have a supercomputer which can solve a very large numerical problem, computational problem, with petaflops computational power. However, we all know that there are millions of more problems which we cannot solve efficiently even with a supercomputer these days. And for the famous example is the factorization of finding factors of given large integer numbers. And around the end of the 20th century, people actually started to think a bit differently than before. So before that, quantum mechanics is applied to technologies, basically, for example, for describing the motion of electrons in our devices. But now people started to think about applying the principles of quantum mechanics at the level of information processing. So this is a kind of, disruptive jump of the concept of quantum mechanics. So not only in the device physics, but now at the level of information processing, we consider like a superposition and entanglement as a useful tool or a useful rule for doing information processing. So, so that was idea conceived by, for example, Richard Feynman and David Deutsch and other people. And when Peter Shor invented his factoring algorithm in 1994, people were really surprised and then jumped into this field to start investigating this possibility. And also Peter Shor kicked away the skepticism about the, impossibility of quantum computing because of the decoherence by proposing quantum error correction algorithm. And so here we use qubit, the superposition of 0 state and 1 state instead of the conventional bit as a unit of the element of the information. Okay, so just to summarize, I propose to call that the 20th century is the century of quantum mechanics, and the 21st century could be a century of quantum information science. So, during the 20th centuries, the quantum mechanics was born and then applied at the level of physics or chemistry or even engineering. And now quantum information science is at the frontier of information science and technology using quantum mechanics as a tool for information processing. And now we are here. And so, but for realizing this idea physically, we really need to solve a big challenge. So, how far we can control quantum systems in terms of the number of degrees of freedom, and also the time and speed, and how long and how fast, and how precise can we control quantum systems. Okay, so there could be many different physical systems which can be used for quantum information processing, like semiconductor electron spins and spins in defects, ions and atoms, and optical photons. But today I'd like to focus on our superconducting circuits. So, superconducting qubit is nothing very complicated. So if we construct a very simple circuit, LC resonator, combining inductance and capacitance, we have a harmonic oscillator or oscillating circuit. And in superconducting qubit, we use a Josephson junction, a tunnel junction between two superconductors as a nonlinear inductance element instead of a regular geometric coil. And then, because of this nonlinearity, the effective potential in this circuit becomes anharmonic, and the quantized level there, becomes, it's difficult, non-equidistance. So here in harmonic oscillator, in the quantum mechanical picture, the energy levels would be totally equidistant. But with this anharmonicity, the energy levels are now separated with a slightly different energy separation. So because of that, we can apply microwave to control the quantum state of this ground state and excited state superposition by using so-called Rabi oscillation, and to create a superposition of the state of the qubit. Yeah, and this simple circuit combining capacitance and Josephson junction can be implemented, for example, in this simple device. So here we have two pads of aluminum on top of a silicon substrate with a scale of dimension of order of millimeter, so it's visible with our eyes. And in between, there's a narrow bridge, and in the middle of the bridge, there's a small tunnel junction between, it's oxide sandwiched by two aluminum electrodes. So, this device, this simple device, is exactly the, say, equivalent circuit of this diagram. So here we obtain this energy levels, and this millimeter scale device behaves as a quantum two-level system at low temperature. So because this is the artificially designed circuit, we can choose capacitance and inductance at will, and the energy scale could be designed whatever we want. So we typically use energy separation between the two states in the range of gigahertz to 10 gigahertz, so microwave energy scale. So the single photon of microwave corresponds to this energy. And then in terms of temperature, this is about 0.5 Kelvin. This is very small energy scale, but still in the low temperature environment, which we can realize in a commercial refrigerator, okay, it's a special refrigerator, we can still cool the system down to the ground state. So superconducting qubit is really a simple electrical circuit. Yeah, and sometimes we call this qubit as artificial atom because as you see, the energy level structure is very analogous to what we see in the natural atom. So in natural atom, we have also anharmonic potential due to the Coulomb potential of the positively charged nucleus, and the electrons are trapped in this potential to create energy levels. So our circuit looks quite similar to an atom. The only difference is the size of the system. The atom is also in an angstrom scale, while our device is a millimeter scale. So because of the difference, the energy scale is totally different. This is electron volt scale, while this is micro electron volt scale. Okay, and also because our artificial atom is much larger than the natural atom, it has a much larger dipole moment. So it couples to the electromagnetic field very strongly. So this superconducting device has very low loss, no resistance, and Josephson effect gives a strong nonlinearity, and the macroscopic size of the circuit gives a strong coupling to the electromagnetic field. Okay, so that's good, but one problem we have is that our qubit couples to many other degrees of freedom in the surrounding environment. So this qubit can couple to, for example, photons or phonons into the substrate or some excitation in the surrounding circuit, and also couples to other microscopic degrees of freedom, like a charge defect or spins around, or like magnetic field noise. So there are many enemies which disturbs the coherence or superposition of the states in the qubit. So, and that's why we have to very carefully protect our system, our qubit, from all those enemies. Okay. So because of that, actually, when we started superconducting qubit experiment at first in 1999, the lifetime of the quantum state stored in the qubit is less than nanosecond, extremely short. So yeah, I at that time I never imagined the progress in the later years. But then in the last more than 2 decades, thanks to the efforts by all the people in the field, we observed that the 5-6 orders of magnitude progress improvement of the coherence time of the qubit. So nowadays, say this is already out of the frame, but the longest coherence time of the qubit would be around 1 millisecond. So 6 orders of magnitude improvement from the beginning. And behind that, there were many technical improvement and better understanding of the physics and design improvement and so on. So yeah, thanks to that, we have now very long coherence time. So now we have very good qubit, and so typically our qubit can be manipulated by within like a 10 to 100 nanosecond time scale. So with a given lifetime of millisecond, we can do a lot of coherent manipulation of the quantum states. So basically many steps of calculation in our quantum computer. So yeah, because of this progress, nowadays many groups around the world have started building small-scale quantum computers using tens of qubits integrated on a chip. So this is, so yeah, probably you remember that in 2019, the Google team announced their quantum supremacy demonstration using 53 qubits out of 54 qubits on a chip. And so they demonstrated that this small quantum computer can outperform any supercomputers on some particular problem, which is very favorable for quantum computing and very unfavorable for supercomputer. But still, it's a big, I would say it's a big milestone showing that quantum computer can outperform the supercomputer. And then following that, other teams started to build small-scale quantum computers. So this is up to 2021, but last year we saw many more qubits integrated on a chip. So quite recently, IBM Group announced that they integrated more than 400 qubits on a chip. And they even put forward their roadmap saying that they will keep scaling up in the coming years. Okay. So, but it's not that simple. So, in principle, we can just make many qubits on a chip and make a larger scale quantum computers. But what matters is that all those qubits have to work very precisely without small probability of errors. And yeah, unfortunately, there's always a finite error probability in our qubit devices. So so having many qubits on a chip, we have more and more probability of having some errors in the midst of the quantum computation step on the chip. So, so we will have some errors happening from time to time in somewhere on the chip. And then to continue the calculation properly without affected by the errors, we have to somehow get rid of this sort of entropy created by the errors. So we need something like this pump to pump it out of this quantum computing chip. So that is what quantum error correction does. And then if you do it properly and continuously and keep the system clean all the time, then we can do very large scale, very deep computational steps. So, so that is called, say, fault-tolerant quantum computing. And for that, we actually need to encode our quantum information not in a single physical qubit, but in a group of qubits, ensemble of qubits in the 2D array, for example. So here, this is a famous, commonly used encoding called surface code, where the qubit information is encoded in the array of 2D array of physical qubit, nearest neighbor coupled. And so here, in between these yellow data qubits, where quantum information is stored and manipulated, we put green and blue syndrome qubits in between. This is to diagnose whether error happens or not in the surrounding data qubits. So this syndrome qubit couples to four data qubits in the neighboring 4 data qubits, and it gives the signal if there were error in one of these 4 qubits. So it will give signal as a parity check signal. So without giving the information about the particular qubit. So that's why even if we do this measurement, we do not destroy quantum information on each qubit, but we just get the say signature of the presence of the error. And by doing this syndrome measurement many places and many times, we can analyze or we can how to say estimate where the error is and what kind of error is, and then we can correct the error for the next step. Okay, but for doing that, we really, the theory said this is possible, but no one has ever fully succeeded it yet, because this protocol requires very low error rate in each physical qubit operation, and also very large overhead in terms of the number of the qubit, physical qubit integrated. So that's a challenge for us. So integrating large number of qubits with a very small error rate for each. Okay, yeah. So nevertheless, since last year, several teams have demonstrated a very small scale surface code encoding and error correction. And so, for example, this demonstration on depth 3 surface code. And the Google team recently demonstrated that the depth 5 with larger surface code could work better than the smaller one. So, so there's some evidence that the error correction is really working. But still, here, not yet, no one has yet demonstrated break-even. That means the encoded logical qubit error rate is becomes lower than the error rate of individual physical qubit. So that has not been demonstrated yet in this kind of error correction scheme. Okay, so yeah, from now on, let me tell you what we are doing in RIKEN in this direction. So we are also working on this two-dimensional integration of the qubit on a silicon silicon chip. And here, our architecture is a bit different from others in the sense that, so here we have the qubit integrated in 2D array on a chip. And then this substrate has many vias, holes through the silicon wafer, and it's metallized by superconducting material. So it's superconducting through silicon vias to stabilize the ground connection and eliminate the microwave crosstalk and stray mode. And then all the wires comes from the back side of the chip in the vertical direction. They are all coaxial cables for microwaves. And then contact probes with a spring touch at the back of the substrate. And so for scaling up, one big issue is the wiring. So you can imagine that if you have a 2D array of qubits, and if you want to deliver control and readout wires for each qubit from the side, you can imagine that many wires have to cross each other, and then we have microwave crosstalks and unwanted effect. So that actually prevents us from scaling up of the chip in a larger size. So here we design our system such that we can basically freely scale up without taking care of all these crossovers, because all the wires come from the backside vertically. Okay. And then on top, we also put the flip chip cover just to suppress the stray mode and crosstalk, and with a superconducting contact. Okay, so this is a picture of the chip. This is for 16-qubit chip with the dimension of 1 centimeter by 1 centimeter. As you see, there are many holes in the chip. And this is 64-qubit chip, 2 centimeter by 2 centimeter, 8 by 8. And so if you zoom up, actually these chips are designed with a unit cell structure. So we have this 2 by 2, 4-qubit unit cell, and this unit cell cells are tiled to create a 16-qubit or 64-qubit chip. And so here we have qubit, this circular shape part with a diameter of 0.6 micrometer or 0.6 millimeter, 600 micrometer. And there's a Josephson junction. So this ring on the inner island creates a capacitance and then connected by a Josephson junction. And there's a readout resonator for each qubit, and also a filter resonator for multiplexing readout for 4 qubits. And there's a capacitive coupler in between neighboring qubits. And so if you zoom up a Josephson junction, we see the 2 aluminum wires overlapping or sandwiching oxide in between. And the Josephson junction is small, 200 nanometer by 200 nanometer. Okay. And on the back side, we also have some structures, ground plane and contact pad. So the contact pin touches here for the control and touches here for the readout. Yeah. Okay. So the cross section is like that. Okay, so for controlling each qubit, we use Rabi oscillations. We apply resonant microwave on each qubit to induce Rabi oscillation between 0 and 1 state, and to create any superposition you want. And for 2-qubit gate, doing conditional operation between neighboring qubits, we use so-called cross-resonance gate, where we apply the resonant frequency of the second resonant frequency of the target qubit to the control qubit. So because those two qubits have different resonant frequency, the resonant frequency on the second qubit is off-resonant from the first qubit, but still induce tiny precession off-resonantly driven. And then, because of the capacitive coupling in between, this precession on resonant with this qubit induce full Rabi oscillation conditioned on the state of the first qubit. So that creates a conditional gate operation in between. Okay, so works on this system. And then for the readout, our qubit is coupled to this readout cavity, the harmonic oscillator. And then because of they are far detuned, but in the perturbative regime, the cavity frequency actually depends on the state of the qubit. So by monitoring the microwave reflection at the cavity, we will see the difference depending on the state of the qubit. That's how we read out the state of the qubit. So we have qubit here, and then the resonator is coupled to the qubit. Okay. So and then this chip, our chip is mounted on a special package with those coaxial cable from the backside and with a spring contact. So here you see many pins from the bulk aluminum, and then we put our chip on this, and then also put the flip chip cover on top, and then press it from the top and to make a contact. So that's how it's integrated. And then it's mounted in our dilution refrigerator with many wires, and so the package is mounted inside this magnetic shield. So you also see other microwave components like low temperature amplifiers, and then many lines and filters and attenuators, so on, and amplifiers at 4K stage. So in total for our 64 qubit, we need more than 100 microwave lines. So that's why you see many cables here. And then we put it in a vacuum can and then cool it down. Okay, and actually we found that developing for constructing quantum computing system, developing superconducting chip is not really more difficult than developing classical control electronics. So we spent a lot of time to construct our custom-made FPGA-based microwave pulse control system, which allows us to control many, say, 112 channel say control and readout, all synchronized. And so this control unit is now connected to our fridge. So, so in this kind of chip, so far we have achieved the control and readout fidelity of more than 99% at the best value. But I have to admit that this is the best value. Not every part is working like that. So, but yeah, we hope that we can manage that in near future. So in the latest chip we have in the fridge now, for example, we have 64-qubit chip. There, coincidentally, 53 qubits are working. And so, yeah, for example, 1 qubit was dead from the beginning, and this 8 qubit cannot be read out because the amplifiers have some issue and producing huge noise, so we switched off. And here are 2 qubit where the frequencies collided, so we couldn't really operate it. So, but the rest of the qubits are working properly, and even though in our device the coherence times are not very good, still we can do some simple operations. And yeah, I also mentioned that here the qubit design is a little bit different from the previous one, but the similar layout. Okay, so yeah, unfortunately, I don't have much more to say about this system yet, so I hope I can tell you more in near future. Okay, so in the last 10-15 minutes, let me switch gear a little bit. So, so controlling, so we want to control a large-scale integrated qubit systems, and so as I said in the beginning, each qubit is nothing but a nonlinear microwave resonator. So in the end, what we are doing is something like juggling microwave photons around between qubits and resonators. And so in that sense, microwave quantum optics is quite essential for understanding the physics and also establishing the technology for quantum computing. So, you know, quantum optics is a field where we treat optical or electromagnetic field quantum mechanically, and then quite often we are interested in the interaction between atom and photons. And so this traditionally studied in atom optics community, where people were interested in the interaction between a single atom trapped in an optical cavity. And then the interaction between this atom and the photon confined in the high-quality cavity was investigated. And when the coupling strength G between the atom and the photon mode is much larger than the other dissipation or relaxation rate, then we can expect that there's a coherent interaction between the atom and the photon, single photon in the cavity. So that's a field called cavity quantum electrodynamics. And later in 2004, the Yale group put forward the new idea of circuit QED, a circuit version of cavity QED. So where we create a microwave cavity coupled to our superconducting qubit. But also, so here we study the interaction between atom and a confined photon. But we can also manipulate photons propagating along the waveguide. So on a microwave circuit, we can simply make waveguide, like a coplanar waveguide on a chip, and where microwave propagates. And if we put the superconducting qubit strongly coupled to the waveguide, one-dimensional waveguide, this two-level system works as a very effective scatterer of the photon. And when for example, the spontaneous emission rate from this two-level system into this waveguide mode is much stronger than other relaxation channel, we can call this also strong coupling of the atom to the one-dimensional propagating photonic mode. So by using this, we can actually control the both confined photon and also a propagating photon very well. So in the last 10 years, we use this idea to control and also detect a single microwave photon very precisely. So for example, we demonstrated a single photon detector for microwaves. So microwave photon has a very much smaller energy compared to optical photons. So usually, single photon detection is much more difficult in the microwave domain. But by using the superconducting qubit, which can be very strongly coupled to the propagating photon in the waveguide, we demonstrated two types of single photon detectors, like absorptive type, where we absorb incoming microwave photon with a kind of artificially made lambda type 3-level atom created with a superconducting qubit embedded in a cavity under microwave drive. And also, we demonstrated quantum non-demolition detection of single itinerant photons. So that means, usually, photon detector absorbs photon and then change into turn it into electrical signal. But here, we do not absorb the photon. The photon is just reflected by the qubit in the cavity, and then the qubit change the phase if the photon is reflected. And then later on, we detect a phase flip. So that means the photon is not absorbed, just reflected, but the presence of the photon is detected. So this kind of detection can be done with very high efficiency. And yeah, more recently, we are working on generation of the microwave photon pulse propagating into microwave waveguide. And for example, here we generate trains of entangled photon as a cluster state, and then characterize this entangled state up to 35 photons in series propagating on the waveguide. And we actually characterize a huge dimension density matrix of this entangled state. Okay. And okay, we still have time. So yeah, another gadget we create from this idea is what we named Josephson quantum filter, where we wanted to protect our qubit from the noise coming from the control line of the qubit. But if we make the coupling between the control line and the qubit very small, we can reduce the effect of the noise. But on the other hand, we have to apply much more power to control the qubit. So there's a trade-off. But here we use another qubit as a nonlinear filter, which can transmit relatively strong control pulse, but which do not transmit spontaneous relaxation from the qubit. So this works as a nonlinear filter to protect our qubit from the noise out from the control line. So this can be integrated for large-scale circuit, for example. And another type of filter which can be used for the improvement of the qubit readout is so by using a multimode structure in the readout resonator, we can create a kind of intrinsic filter inside this readout resonator. And that filter actually really suppresses the decay of the qubit. So that means we can even stronger couple the readout filter to qubit. And because of this strong coupling, we can read out the qubit much faster and much stronger and have a very nice readout fidelity and in a very short time. So here in this three-dimensional architecture, we achieve like a 99% fidelity, but even later we implemented it in a 2D chip, and here we have even better number, like within 36 nanoseconds we have more than 99.96% readout fidelity without affecting the qubit state. So this kind of microwave optics idea can be implemented in integrated circuit in future to further improve the properties of our circuit. Okay, so this is the last slide. So here, this is the idea of a new 2-qubit gate between fixed frequency qubit. And so here we use another fixed frequency qubit as a coupler. And because of the nonlinearity of this coupler element, we can induce some higher order transition between 2 qubits, which can be used as a 2-qubit gate. And this could be advantageous in terms of the driving power and also the mitigation of the frequency collision and also the residual interactions. Okay, so I think it's almost time, and so let me summarize my talk. So today I explained our activities and also some other groups' activities towards superconducting quantum computing. And so superconducting qubits is nothing but nonlinear resonator circuit and using Josephson effect, and it behaves as an artificial atom and realized in electrical circuit. And so for superconducting quantum computing, we really need high fidelity control of a quantum system with a huge dimension of the Hilbert space. So that's a really challenging problem. So we have to fight against the decoherence, and also we have to devise nice architecture for the scaling up and for future fault-tolerant quantum computing. And microwave quantum optics is a very nice framework for developing all those techniques and possibly new interesting physics. And I didn't have time to explain about hybrid quantum systems, but that I mean that this idea of artificial quantum systems in superconducting circuit can be extended even further to other physical systems, especially in the microwave domain. For example, we can couple our qubit through microwave cavity with mechanical oscillators or ferromagnetic resonance or magnonic excitations, and to do a single photon or single phonon or single magnon control or measurement and so on. So that enables us to investigate which we couldn't observe before in those condensed matter systems. Okay, so that's all. Thank you very much for your attention.
Yes, thank you to Yasunobu. Here's a present from NWO. It's a physics game that you can play. And I hope you will enjoy that as much as we enjoyed your talk. Thank you again to Yasunobu.
Yeah.